Hello, my name is Krishnali Lahane. In this presentation, I will talk about my project titled Clustering Food Safety Alerts and Predicting Urban Footfall. The project focuses on two real world problems. First, clustering food safety alerts. Second, predicting urban footfall using machine learning. I used unsupervised learning for clustering and supervised learning for regression, and I evaluate both approaches carefully. Urban systems generate large and complex datasets every day. Because of this, manual or rule-based analysis is no longer scalable. In food safety, alerts need to be analyzed quickly to identify potential risks early. Similarly, predicting pedestrian footfall is important for city planning, transport, and public safety. This is where machine learning becomes useful. It allows us to analyze pattern in data and extract insights that are not easily visible using traditional methods. This process this project is guided by four main research questions. First, can clustering reveal meaningful patterns in food safety alerts? Second, do these clusters align with official risk decisions? Third, can urban footfall be predicted using historical data? And finally, which regression model performs better for footfall prediction? Based on these questions, the objectives are to be apply clustering to RASF alerts, build regression models for footfall prediction, and evaluate all models using appropriate methods. I used two different datasets in this project. The first is RASFF dataset, which contains food safety alerts from European Union. It includes the text description and categorical attributes. But there is a target, there is no prediction target. So this dataset is suitable for clustering. The second dataset is urban footfall dataset. It contains time-stamped pedestrian counts from multiple locations. Here the target is numerical. So this dataset is used for regression modeling. This slide shows the overall system architecture of the project. There are two parallel workflows. On the left side is the footfall prediction pipeline. On the left side is the footfall prediction pipe. On the right side is the RASF alert clustering pipeline. Both workflows start with data collection and pre-processing. For regression models are trained and evaluated using MAE and RSME. For RASF alerts, text vectorization, dimensionality reduction, and clustering is applied, followed by cluster evolution and interpretation. This diagram shows the full process for raw data to final insights. The methodology follows a CRISP-TM inspired process. I use separate pipelines for clustering and regression because the nature of the problem is different. Careful data processing and feature engineering are applied in both the cases. Model selection is based on task characteristics, and evolution is designed to avoid data leakage, especially for the time based footfall dataset. This slide shows the clustering evolution for RASF alerts. The heat map displays cluster composition by risk decision. Even though risk labels were not used during the clustering show strong alignment with official risk decision. This indicates that the clustering model is able to group alerts with similar risk characteristics, so the clusters are meaningful and not random, which supports the usefulness of clustering for exploratory food safety analysis. Here I evaluate the regression model used for footfall prediction. I compare linear regression and random forest using MAE and RSME. Table shows the random forest performs better with lower error values. This indicates that pedestrian follows non-linear patterns that linear models cannot capture effectively, so random forest is more suitable for this task. The key findings of this project are that clustering can identify risk-relevant alert groups, and random forest outperforms linear regression for footfall prediction. Footfall patterns are also strongly time-dependent. However, there are some limitations. Clustering is affected by class imbalance in the food dataset. Footfall prediction is less accurate during peak hours. Also, external factors such as weather and events are not included. To conclude, this project shows that machine learning provides valuable insights for urban analytics. Both clustering and regression approaches were effective for their respective tasks. In the future, advanced NLP techniques could improve alert analysis. External data such as weather or event could improve the footfall prediction. Finally, this model could be deployed to real-time dashboards for decision support. Thank you very much.